Hello everybody, welcome back to my Surviving APCSP course. This was the second video I'll be doing, and of course these videos aren't in order, they're by topic. So today we'll be covering the base 8, base 10, and base 2 systems of notating numbers, and all of my content will be based on explaining Mr. Millard's APCSP content at American High School in Fremont, California. And let's begin. So what is a base system? A base system is simply a notation we use to note down a number. So for example, let's say we have the most common base used, base 10, also known as the decimal. The base 10 has the digits 1, 2, 3, 4, 5, then 6, then 7, then 8, then 9, before finally repeating into 10. Okay, so these digits here, 1, 2, 3, 4, 5, 6, 7, 8, 9, are what we use in the base 10 system. Okay, so I'm going to go ahead and I'm going to list the base here. So base 10 system. This base is also called the decimal system. And I know I'm going to record this line here in a moment, but we'll come back to it later. The second most common one, or the one that you'll need to know for this, will be base 2 system. The base 2 system consists of the digit 0 and 1. Oh, I should add a 0 up here. So essentially what you'll have is 0 and 1 before the cycle will repeat back to whatever number that'll come after this. So this is called the binary system. Binary system has only 2 numbers. Next one will be the base 16 system, also known as the Hex system. The Hex system. And the Hex system gets really weird in that you will have your usual 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but then you'll go into 10 back up here. So 9, 10, and then 11, and then actually you might think it's 10, but that's incorrect. What we'll notate 10 as is an A. So 10 is an A, 11 is a B, 12 is a C, 13 is a D, 14 is an E, and 15 is an F, before finally repeating back. Okay, so as you can see, oh, I got tilted there, but as you can see here, essentially what it is the base 16 system will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, and these are just the most common bases you need to know, just the different ways, or the most common ways you can note base systems, which is decimal, binary, and hex. All right, so as we can see here, an important pattern to note is that when it comes to the base 10 system, the highest number will be 9. When it comes to base 2 system, the highest number will be 1. So it's whatever base it is minus 1. When it comes to 16, it'll be 15 characters. So if we count, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, 15. 15 characters, right? So that's a very basic thing. So let's start with binary. Binary is one of my favorite ones because a lot of people find it complicated, when in fact, you can do this in a very simple way. So how do you convert a number into binary? All right, and let's start the other way. How do we go from binary into a number? How do we go from binary into a number in the base 10 system? Again, I'll write the base down here. So what we'll want is, let's say we have the binary number 10011. Seems like a fun number to me. The way we'll convert this into the way we'll convert this into decimal system will be to say that every 1 equals a yes, and a 0 equals a no. And I'll expand upon this idea later, but all you need to know is 1 is yes and 0 is no. Now, what do we know about how base... Now, let's go over to the side here. What do we know about how base system works? The base system works based on powers. So, for example, in the base 10 system, the first place is 10 to the 0, then it becomes 10 to the first, 10 to the second, and 10 to the third, etc. So, as we can see here, that the base 2 system works just like the base 10 system, and that goes from 2 to the 0th power, to the first power, to the second power, to the third power, just like the base 10 goes from 0, 1, 2, 3, etc. So let's say we have this number here, this binary 10011. Essentially what we want to do is we want to break this up into its individual components, where we'll say that we'll have 1 over 2 raised to 0, 1 over 2 raised to 1, 0 is associated with, I shouldn't say over, 0 is associated with 2 raised to 2, 0 is associated with 2 raised to 3, and 1 is associated with 2 raised to 4. Now, going back to what we said here, where 1 is a yes and 0 is a no, a 1 will tell us to add that power, to add that digit, and a 0 will tell us not to add a digit. You'll see what I mean. So for example, 2 raised to 0 is 1. And by knowing that this is 1, 2, 4, 8, and then 16, we can go ahead and do it like this. This number is essentially telling us to add 1, add 2, don't add 4, don't add 8, and then add 16. So essentially this number, so 10011 in base 2 equals 16 plus 2 plus 1 in base 10, which should be equivalent to 19. So 10011 in base 2 is 19. So let's continue on to our next topic, which will be how do we convert from binary, or how do we convert from base 10 into binary? And we'll use the same example of 19. So we're going to go now from decimal into binary. Essentially what we want is what we'll do is we'll do a trick I like to call the remainder 2. Essentially what we'll do is we'll take 19, and we'll put it at the very right side of our paper. Okay? And what we'll do is we'll divide 19 by 2, and then round down. So 19 divided by 2 would be 9.5, but then we'd round that down to 9. Do the same thing here, where it would be 4.5 would round down to 4. This would go down perfectly to 2, and this would come down to 1. And essentially what we want is on every odd number, we want to go ahead and put a 1. And on every even number, we want to put a 0. So we went from 19 into 9 into 4 into 2 into 1 by dividing. And since 1 is a odd number, we'll go ahead and put a 1. 2 is even, 4 is even, 9 is odd, and 19 is odd. So as we can see here, this checks out to what we did before, where 1011 is 19 in decimal, and we did the same thing here, where the top one is the decimal, and the bottom one is the binary. Pretty simple. So all you got to do is divide by 2, remove the remainder, divide by 2, remove the remainder, divide by 2, remove the remainder, and then you get 1001 in binary. So that's pretty nice. This trick works with every number, and it's much easier with even numbers. So in summary, decimals, you divide, whatever there's an even number, you put a 0. Whenever there's an odd number, you put a 1. Okay, so let's go ahead and move on to hex. Hex is an interesting case. And when it comes to hex, I'll teach you 2 methods to converting. The first one is the way I like to call hex complicated. Hex complicated is an interesting scenario. Hex complicated works by, let's say I have, by using the definition of a base system. So let's say I have the number 100 in base 16. Though number 100 in base 16 is quite simple. Essentially what you're going to do is you're going to say that 0 is in the 16 raised to, part of the 16 raised to 0, okay, so or essentially 1. Okay, so we can rewrite this into 0 is associated with 1, another 0 is associated with 16, and the last digit is associated with 256, because 16 times 16. And essentially what all this is saying is that, hey, just add up the numbers by multiplying. So what you'll do is you'll take 256 times 1, 16 times 0, and then 1 times 0, and write their values. And then you'll add them up. So 100 in base 16 equals 256 in base 10, as you can see here. So I have gone ahead and set up another problem, which is if I have F01 in base 16. Essentially, we'll go ahead and do the same thing. We know that F equals 15 when it comes to hexadecimal, referencing back to the previous page. So essentially what we're doing is we're going to do 256 times 15 equals something. We'll take 16, multiply that by 0, and say that equals something. And we'll take 1 and multiply it by 1, right? So what we'll go ahead and do is then we'll add up our values. So this will be 3,840 if I'm not mistaken. This will be 0, and then this will be 1, totaling up to 3,841. So essentially, F01 in base 16 is the equivalent of 3,841 in base 10. This is the hex complicated method, in which all you do is you keep writing powers of 16, convert, multiply, add. But this can get very tricky. For example, if this had been a larger number, if I had, let's say I'd gotten F000000001, I would have to do some extremely large power of 16 times 256, which can be a bit painful. So what we're going to go ahead and do is we're going to do the hex binary method of converting now. The hex binary method, as I like to call it, by the way, most of these terms, like my methods, are names I came up with, so don't use those officially on a test, don't quote me. But the hex binary method is very simple. Let's say I have my whole trend of F01 in base 16. We can go ahead and say that since 2 raised to the power 4 equals 16, for every digit that exists in base 16, there are 4 digits that correspond in base 2. Okay, so what does this mean? So we know that F is 15. So we're going to go ahead and convert this into base 2. And what we can go ahead and do is we can create a bit table. A bit table will work like this. For every unit or every character that we have in our base 16 system will be represented as 4 numbers in the base 2 system. So we'll go ahead and draw our line. So 1, 2, 3, 4, that composes of the F block. We have 1, 2, 3, 4, which composes of the 0 block, and 1, 2, 3, 4, which composes of the 1 block. Now what we'll go ahead and do is we're going to represent F, or 15, into base 2 notation. And what I'd like to go ahead and do is write these values into my bit table. And then it becomes very simple from here. So essentially we want to make 15 through some combination of these numbers. Well, how are we going to do that? Well, let's start adding. So we know that 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So 1, 1, 1, 1 is how you represent F, or 15 in base 2. So this row over here is base 2. Keep that in mind. Okay. Next, what we're going to go ahead and do is take this 0. 0 will represent 0. So this will be 0, 0, 0, 0. Okay. And then we'll go ahead and have 1. 1 we can represent by putting 0, or rather a 1 here, because we want 1, 1. We want to add 1, and then we don't need anything else. So essentially, F01 in base 16 is equivalent to 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1 in base 2. And as you can see here, all I did is I took F, which is 15, converted that to base 2, took 0, which is and converted it into base 2, and 1 and converted that into base 2. And then finally, all I have to do is we can use our technique from before and convert this into decimal, and then you'll have hexadecimal into binary into decimal. So let's really quickly go ahead and do this. So using our yes, no, no, no trick, we find out that indeed this number is 3,841 in decimal. Huh. Okay, so in recap, and don't worry, there will be timestamps for everything, so, you know, go ahead and check those out. So, recap. To recap this, essentially what we have is that when converting from binary to decimal, a cool trick to use is the yes/no trick and add. From going from decimal to binary, a cool trick to have is the divide, remainder, even or odd. Okay, so those are for the binary ones. Then we have the hex complicated, which involves adding powers of 16. And then we have the hex binary, which essentially says that uses a bit table, and converts individual digits. It's not really a digit though, is it? And then, yeah, I guess that's about it. I'd like to highlight, I think this is the most important, these are the most important parts. So the hex binary and my, let's see, decimal to binary, those are the big ones. And those are what I'd like to call big brain methods. So, yeah, guess that's the video lecture. Feel free to shoot me any questions, and go check out the r/Millardism subreddit and post some questions there, and I'm sure people will be happy to help you. All right, enjoy.